Now let's take a look at example 2. Here I state a fact. The U.S. Census Bureau reported that the average, notice here, specifically the average household income as of March 2014 was $72,641. Now, if I actually go ahead and I try to locate roughly where that is over here in the picture, that's going to be somewhere in the range of, I don't know, let's see, maybe I'll color it in red, but this value would kind of be somewhere maybe, let's see, I think that's about 75, so I think it's going to be somewhere around this bar right here. Okay, so this is kind of like where my average is going to be located here. Now, this is a fact. This is not in question. If you were to add up all the numbers that they got, divide by how many that they had, that came out as the average. But notice that I have an interesting question on this first bullet point, which is, why might this number, this red average, not be a good representation of a typical household income? Well, at first, this is kind of strange, right? Because isn't the goal of an average to tell me kind of what's standard? I mean, that's again why we ask instructors, like, what was the average exam score? Like, we want to know what seems to be the typical performance. But what's interesting here is that we can see kind of rolled up in this question that the average is not always good. Well, why might the average not be good? Why might it not be good here? Well, if you think about it for a while, there might be some things that you start to notice about this picture. First off, there are certainly a lot of people that are making less than this average amount. A whole lot of people, right? I mean, look at how many over here. Now, there are some people that are making more. And in fact, there are a lot of people in these final categories that start to, say like, 200,000, 250,000 and up. Right? So all the people that are making, like 6, 7, 8 figures, they're over here. They're over on the side. There's a decent percentage of them, 2% or so. And so we can really start to think about the fact that averages become very unstable. And that's actually what I'm going to start to write here. See if you could understand the following explanation. I'm going to state here that the very high incomes, right? Like people like the Jeff Bezos of the world, right? He's the owner of Amazon, right? I mean, he's making billions of dollars a year. Think about what that's going to do when you put his income into this average calculation, right? So, maybe somebody that's making, $40,000 a year. Someone else is making $100,000 a year. Someone's making $70,000 a year. And then Jeff Bezos comes in and he's like, hey, I'm making, $10 billion a year. You're like, whoa, like that average calculation is going to get very skewed very quickly. So the very high incomes can be seen or can seem to actually go ahead and throw off what the typical income, let me word it that way, can throw off what the typical income looks like for most people. Right? Again, you can think about the actual calculations themselves, right? Again, you take that person who's making 50K, you take someone that's making 100K, you're thinking about adding these up, you're going to take an average, right? And then you have someone in there that makes, like 100 million. And you're like, okay, add those up, divide by 4, right? Like that number is going to skyrocket up towards that 100 million. That really big value is going to pull everything up. And so what we see here is that when calculating averages, things get very unstable. You can see the same thing in when you think about test scores in a class, right? Maybe I'm trying to calculate test averages. Maybe you have a friend that got a 75% on an exam. You worked super hard, studied your brains out. You got a 90%, right? Maybe someone else in the class got an 85, and so you're thinking like, wow, okay, so the average, I don't know, maybe it's going to be in the 80s somewhere, and then all of a sudden you say, oh wait, and yeah, there was one person that didn't do anything. They got a 1%. Well, think about what that 1% again is going to do to the average. That super low number could also throw the average off drastically. So what we see here is that the average is rather unstable. When you have really high numbers or really low numbers in a data set, the average just kind of starts fluctuating all over the place. However, there could be a value that might be a better measure of a typical household income, a value that doesn't move around as much. And that value here is actually going to be the median. What we'll see is that the median value is actually even noted right here in the picture. The median value is like indicated by this bar over here. And I did a terrible job of outlining that bar. But right, this bar right here is kind of representing where the median is. And that's a much more representative value. Notice that medians, since they are just focused on finding the center of a data set, are not often going to be concerned with extremely large values. So notice again, if I had a bunch of different income levels that look like this, well, by having these three values, 75K is the median. Well, notice if I change this 100K over on the side to something like 100 million, well, my median income stays exactly the same, right? It hardly shifts at all. Now, if I had something like 100K and then I added on somebody that, say, makes $90 billion a year, well, notice that my median went from 75 to maybe somewhere between 75 and 100, right? I'd have to average those again, but that's still not a very large movement. Way smaller of a movement than what would happen if I calculated the average of the first three and then the average of all four. So this becomes very, very interesting to see that when I have really high and low values, or really high or really low values in a data set, the average might become unstable. However, the median seems to kind of resist the urge to slide around and vary a lot. Well, take a look then down here, because what we'll see is that we can kind of connect this idea to the notion of shape. So what shape might the distribution need to be so that the actual average would be reliable? If really high values in the data set kind of pull the average up, then you can maybe start to think I would kind of need something on the other end to like pull the average back down. Like for every person that makes $1 billion a year, I might want someone in extreme poverty to kind of balance them out. That might be helpful. If I'm doing averages of test scores, for every person with a high 90%, in the super high A's, I might want someone with like a really low F to try to balance them out. And if you think about the shape of the distribution there, that would mean that we would want a symmetrical distribution. Right? Because a symmetrical distribution kind of has like an equal dispersion, like down here, of high values and low values. So this brings us to an important definition now that we have at this point. A numerical summary of data, no matter what it's describing, whether it's measuring something about a center, whether it's measuring something about spread, I can say that numbers that describe data can be called resistant if extreme values, very large or very small values relative to the data, do not affect the value substantially. So notice that when we talk about the idea here of what we've seen up above, we have found that the median, and I'll go ahead and write this right down here, the median is resistant because when I had those really high or low values in the data set, I didn't end up with the median changing all that much. It kind of resisted. It held fast to its original value. I can then say that the mean is then certainly not resistant. It moves around all over the place. So down here I have three different pictures related to three of the different shapes that we've talked about in the last section. And we can kind of see again what's going to be happening based on this idea that the median is resistant and the mean is not. I'm going to start with the symmetrical version here first. Notice in the symmetrical version, my median should be right there in the middle. And my mean, again, is going to be kind of balanced out by these low values and these high values that kind of occur on either side. And so it's going to be the case that the median and the mean are going to roughly be equal to each other and kind of both fall right on this center line. Notice this will be a little bit different if the distribution is skewed left, because if the distribution is skewed to the left, then these really low values are going to be dragging the mean down, right? They're going to bring the average down. And so the bar here on the left would represent maybe where a mean would fall, whereas the median would not have been pulled down, and so it would have been a bit farther to the right. Notice the exact same thing begins to happen in our picture over here with skewed right. If there are very large values in the data set, that's going to pull my average up, kind of like it did in the picture up above. And the median, again, is going to kind of hold fast to its original value and not move very much. So this kind of gives us a sense of where my mean and my median actually exist. And I can see that in this skewed left, my median is often going to be a higher number than my mean. Symmetrical, they're going to be roughly equal. And in skewed right, the median's likely to be smaller than the average. So hopefully you can see here that, again, we're linking the idea of means and medians to shapes of distributions. And we ultimately have a desired preference for when to use a mean or a median to describe a data set. If a distribution is roughly symmetrical or bell-shaped, then the preferred measure of center is going to be the mean, the average. But if the distribution is skewed, then I would like to use the median. Because in a skewed distribution, the mean can get thrown all out of whack, and I want to make sure that I have a value that is going to hold fast and resist those extreme values. So this right here is really important. We're going to see in a lot of assessments in this class that this is an important question. Can I link together the ideas of what particular shape goes with what particular type of central tendency measure?